Got it. All right. Thank you, Kate, for inviting me to give this talk. Thank you, Hugo, for a wonderful introduction. So happy to hear that somebody enjoys reading my papers. Most of the feedback I get from my immediate family is it's really boring and I didn't understand it. So it's nice to hear that from people that do understand it, they also don't find it boring. I could say the same about Hugo's work too. But today I'm here to give a talk about sort of a high-level overview of supporting spatial navigation. And my sort of goal for this talk today is really to tell you about some of the work I've done on what I'll talk about as navigation tools. And we're here, right, in this seminar because presumably we think that human spatial navigation is important to understand and important to keep intact as best we can. And so, to begin, I'd like to offer just one small story that was in the news a little bit recently to give an example of the incredible lengths that humans have gone to escape our reliance of our own, perhaps faulty cognitive navigation architecture. There we go. So some of you will already know where this is going, but this fellow here is Ernest Shackleton. He is a world-class explorer from about 100 years ago, was one of the first explorers, sailors to lead an expedition to the South Pole. He almost made it, but on his most famous adventure about 100 years ago, the Endurance, his ship, became entrapped in pack ice, causing his crew to have to basically scurry away on lifeboats because the ship was totally crushed. Incredibly, in another realm of science and navigation entirely, the ship was actually just discovered at the bottom of the Southern Ocean a few weeks ago. So that was why it sort of popped into my head. But the amazing story of this journey is not just that the ship got lost out to sea and was discovered 100 years later, but rather what happened after the ship became crushed. So this is a map that I found showing the incredible sort of two-leg journey that this crew made. So you can see the sort of Endurance route that it had taken here in red, and the spot where the ship had basically drifted into ice and sank. And what you can see here is that first the crew was able to sort of dash away on lifeboats, making it to Elephant Island, and then plotted a really incredible escape route to South Georgia, where they were eventually rescued. And the sort of hero of this story is Frank Worsley, the navigator of the time, right? And this is actually, this term navigator, some of you probably know this better than I do. The navigator, this was a highly skilled position. So Frank was not on his iPhone using GPS to find his way to to South Georgia to be rescued, right? Instead, Frank Worsley was using tools that required an incredible amount of training to navigate through what I can only imagine looked something like this, right? Treacherous waters, very few cues to do so, perhaps foggy, right? So his reliance on his own sensory apparatus could not basically be trusted, right? So what was Frank Worsley doing? Well, fortunately for Frank Worsley, very intelligent people around then and before had done what humans do, right? Create tools to help them think better, think smarter, right? Rather than work harder. So Frank Worsley had access to a chronometer, a sextant, and a star map, but probably a number of other tools that he was specialized in that required an enormous amount of training, by the way, to use. And also, by the way, that likely required years and years and years to perfect, to understand, right? So this story indicates a couple things. One, it indicates sort of at a basic level how important spatial navigation is, right? How critical it is to be able to know where we are and where we need to go. It's in some cases critical for survival, and not just in the Southern Ocean, but in our daily life, right? To quickly find a hospital, or to remember where your child's school is, or to explore a new city but know how to get back to your hotel, right? So few of us, I think, use sextants. If anybody's an expert, I'd love to hear from you. But today we've developed tools that are a little bit more user-friendly, that require a little bit more sort of automated processing, if you will, in order to support navigation by, in essence, transforming the local environment into orientation and location. Right, so that is the basic process, and that's sort of the basic thesis that I'm going to explore today across a number of different tools. Now, I'm not going to, sorry to disappoint anybody, but I'm not going to be talking about chronometers. I'll be talking about some of the more modern navigation tools that you're likely to find because, well, these are the ones that we use. So I'll talk a little bit about signs, right? I'll talk about maps, and I'll talk about compasses. All navigation tools that you're likely to use, that all of us likely have in devices that we have on our person at all times, and that occur broadly around us in the world to help show us where to go. And so what I'd like to do today is to talk about each of these sets of tools in varying amounts of detail, to really answer the question, how do they work? And what do we mean by work anyway? Right? So how do they support navigation? And if they do, what exactly do we mean when we say we're supporting navigation? So to think about this in maybe a more modern context, let's say that we're all John Travolta these days, lost and not really sure where to go, right? Modern navigation tools work by, in some sense, helping John, showing him the way to go, right? And these tools might look something like a helpful exit sign or a compass that indicates which direction John is facing in the world and allow him to infer which direction he might go, or maybe a map of the layout of his apartment, right? And all of which would have the goal of helping John Travolta become slightly less confused about where he might need to go. So do navigation tools work? Well, so I'm going to cover these three sets of tools. So to introduce them just briefly here before we dive into the actual research itself. So the three sets of tools we're considered today: signs, which have the potential at least to sort of show the way to go directly, right? Immediately in our environment, we want to be able to extract that information, not about where we are, but about where we need to go. Maps, which can provide a metric information sort of overview of an area, giving us not necessarily our own location and orientation, but allowing us to establish a broader sort of cognitive map, if you will, of that broader space that we're in, of the large scale environment that we can't directly perceive. And compasses, which offer a reference direction. Right? So each of these different kinds of tools provides a different sort of information. So we'll work our way through each one by one, and I'll talk a little bit about some of the data that I've collected showing just how they work, if they work, and what we might need to do to move beyond just supporting navigation behavior. So just to repeat that main thesis, navigation tools will work by supporting navigation, by transforming the local environment into something like orientation and location. So one of the things that I'm sort of not going to talk about too much in the first part of this talk is the idea of improving navigation behavior. Right, so I want to early in this sort of introduction, I want to contrast these two ideas because I think it's really important for thinking about the ways of providing people with navigational assistance. Right, so if we're thinking about supporting navigation behavior, we can provide additional spatial information. We can ease the cognitive burden of spatial navigation, make people think about it less. We can draw attention away from our own body-based signals, right? We don't have to worry so much about which direction we're facing or where we're looking. We can just focus on the tools that we have at our disposal. But we might see limited transfer once those tools are taken away. Right? I think this is the key point, right? So when I talk about support, what I really mean is allowing people to more effectively navigate their space, not necessarily skills that allow them to navigate new environments on their own more easily, or even learn environments more effectively. So later on in the talk, we'll see some of the ways that these tools can support navigation behavior, but I think we have a bit more work to do on actually improving navigation behavior. Okay, so beginning at the beginning, very good place to start. We will start off by considering signs or spatial directions, something that you might see plastered somewhere in an airport to tell you where to go, right? So how do signs support navigation? Well, one challenge that in general navigators have to solve is extracting information from the environment about which way to go. Right? And sometimes for even relatively simple scenes, this can be a difficult thing to extract that information about which way you need to turn. So for instance, I used to live in Philadelphia, and one of the questions that I would, well, it's always at the top of my mind is where would I go in order to find ice cream? And having lived here before, I happen to know that the answer is to make a sort of slight left turn onto Ridge Avenue here. But note that the problem that my visual system has to solve is already quite complex, right? So we're supporting spatial navigation here by helping, by reducing the complexity of this scenario, right? I know I need to make a slight left turn, but this is a complex problem that my visual system has to solve. Now, fortunately, spatial directions, signs, perhaps my phone GPS, would give me some of the same information, but in a different form, right? In what we're going to call schemas, or an arrow that points the way to go, or even words that do the same thing, right? A slight left direction. Now, there's two sorts of issues here. One is, do these spatial directions actually provide more easily extractable information for me? But then also, how does my brain convert across these different formats to do what I actually need to do, which is make the actual slight left turn to go get ice cream? So just to cover each of these, what I refer to as formats in a little bit more depth here, or just to be a little bit more formal about what I mean. So we can think about images, sort of representative of the visual scene that I showed a minute ago, right? Images contain all of the information that we would need to navigate around, the precise information, right? We need to actually navigate, but they also have a lot of extraneous info, right? They have the color of the trees, color of the buildings, they have whether or not cars or people are around, a lot of pieces of data that I don't actually need in order to know which way to go. Now, on the opposite end of the spectrum, we have words, right? Words have very few extraneous features that actually define what they are, maybe color or maybe font, but they're non-iconic, right? By that, I mean there's no perceptual similarity between the words sharp right and an actual sharp right turn. Now, a nice middle ground would be something like schemas, which I'm defining broadly. You can kind of just think of schemas as arrows, but really they have most of the extraneous features abstracted away. Maybe just color and a little bit of the size of the arrow is left, and they're still iconic, right? They look like the kind of sharp right turn we might actually need to make in the world. And by that, I mean they share some perceptual similarity here. Now, just a brief note, although this talk is mostly focused on spatial navigation, I'll note that this is a general problem that the cognitive system has to solve, right? If we want to try to escape predators, it's a lot harder to extract an alligator in its natural habitat than it is to say, oh, a sign with an alligator on it, or even a sign telling us to beware of alligators. And similarly, for human actions, we can easily extract information from schemas and words that give us the very complex information about what that human action actually looks like, right? So it is a sort of general problem. Here we're going to dial in and focus on spatial navigation for obvious reasons. They have a, yeah, these signs are just everywhere in Florida, so there's no escaping alligators. All right, so to study this question, I developed a stimulus set that sort of controls the visual complexity across these different formats, while also giving us a large range of exemplars to choose from. So we selected these 7 spatial directions based on some previous research, but also based on sort of inspired by Google Map directions. And we collected images of roads that were turning across those various directions. We developed a set of schemas, so arrows or chevrons, which were overlaid on the phase scramble backgrounds of the images, in essence, to control their visual complexity, to not make them super simple. Again, in those 7 different spatial categories. And finally, a set of words. And the different exemplars would vary slightly in their visual properties, so different color, different sizes, different scramble backgrounds, that sort of thing. So we had a large range of each of these kinds of stimuli. So the first kind of question that we considered in this area was, is there really any advantage to the non-image schema, right? Are we just better off just showing people images of the exact terms they need? Or is there some advantage to actually reducing the complexity of these things? So in study 1, we considered whether spatial directions led to essentially a benefit in working memory. So to do this, we ran 48 subjects, right-handed English-speaking undergraduates, very young, healthy folk, in what's called a fancy term rolling one-back task. But basically, it's a same difference task where you say whether the spatial direction is the same as the thing that you just saw before. I'll show you an example of it in a second. And here we were most interested in reaction time, right? So under what conditions was somebody faster to extract that spatial direction? So the task itself looks something like this. On each presentation of a stimulus, the participant was instructed to say whether that image was the same or different from the one that had just preceded it. So if you're shown a spatial direction, well, this is just the first one, so it's a right. So on this next one, you'd have to indicate whether this is also a right spatial direction, and the answer is no, it's different. And now you have to indicate whether this was the same as the one that you just saw. So the sharp right is not the same as the ahead that you just previously saw. So that would again be different. And again, another stimulus, and this time the sharp rights are the same, right? So this is a sharp right, and the one that you just saw was also a sharp right, right? So we collected a large number of trials, and you'll note, of course, that the trials could be of any format. Right, so sometimes participants would go from a word to a word, but sometimes they would go from a schema to a word or an image to a word, right? So not just how fast are you to extract the individual format, but how fast are you to extract converting between formats. Okay, so I'll be plotting reaction time here. So the higher up the y-axis you go, the slower you were overall. And first, I just want you to focus on these image bars. So along the x-axis are the current trial format. So that's if you see an image, how quick were you overall? And each of the 3 different bars is just what the previous trial format was. So you can see images overall were fairly slow compared to schemas and compared to words. So schemas and words schemas were a little bit faster than words overall. So again, just comparing kind of across all 3 of these. But what was notable was that images were the slowest, right? When you were confronted with an image, this caused a lot of delay in your indication of whether that matched the spatial direction that you had just previously seen. Now, we can go one step beyond that with these data because, as I said, we varied the previous trial format as well. And one of the things we're interested in here is whether there's a specific advantage for the within format case, right? So if you see a schema and then another schema, does that give you a particular advantage compared to, say, comparing 2 words to each other or comparing 2 images to each other? So on this next slide, for simplicity, I'm just going to plot the same format advantage. And in essence, you can think about this as how much better is it for you to have seen the format that you are currently seeing? So in other words, going from an image to an image, does that have any advantage than going from a schema to an image or a word to an image? Right? And similarly for schemas and similarly for words. And the takeaway here is that this same format advantage is greatest for our abstracted formats, right? For these schemas and for these words, for things that you might typically see on signs, right? Whereas images, in part maybe due to their complexity, are a lot more difficult to map even the same spatial direction, right? So a slight left image to a slight left image causes a little bit of computation, right? It requires you to actually think about that scene a little bit more than you would the other kinds of formats. So we ran this in another sort of cognitive psychology approach. So rather than looking at working memory, we looked at here visual attention, right? So this isn't necessarily how easy it is for you to compute the two spatial directions from each other, but rather how quickly your attention can be cued to an area of space. So here we ran 50 English-speaking undergraduates. We used a classic paradigm called the Posner queuing paradigm. There are 120 trials here, so 40 per format. So we had 40 for images, 40 for words, and 40 for schemas. And again, here we're most interested in reaction time. So this test worked a little bit differently. We would display for an initial display of just 2 boxes on the screen, really simple, for about a second. This would then be followed by a cue. That cue would be either a left or a right image that could be a left or a right stimulus that could either be an image, a schema, or a word. And so in this case, each of these cues was indicating left, but we also had some that could indicate right, and subjects would only see one of these at a time. This was followed by a delay period of variable length, and then a target would appear. So one of those 2 original boxes would light up either on the cued side, which would be a valid trial, in this case, the left side. 15% of the time, though, there would be invalid trials, meaning the box would light up on the right side, or a catch trial. So on catch trials, nothing would appear, and that was just to make sure subjects weren't randomly pressing their buttons around. Now, what we're most interested in here is this cue validity effect, right? So how much faster are subjects to respond to the cued side when compared to the non-cued side, right? So they had to indicate which box lit up, and the valid cue, you should be faster than, right? So actually, I think this subtraction is in the other order. But the basic idea is if the cue cues you to that side of space more easily, then you should have a stronger cue validity effect. And what we found was that for schemas and words, we find attention was cued the quickest, right? We had the strongest cueing effect for schemas and words. Images, interestingly, didn't seem to cue attention all that strongly at all. We're actually following this up with a couple of different experiments to capture some of the variability in the images themselves. So stay tuned on this question. There's a bit more going on. I'm looking at a comment from Kate that says, might same format advantage happen because it is necessarily different and don't need to process as deeply. So I think that's precisely what's going on. So let's hold that thought until we get to a little bit of the brain data that can speak to this. Okay, so far I think the behavioral data make a pretty clear case that signs support navigation behavior by offering easily extractable spatial information. So does the brain process spatial directions in images differently from schemas and words? So there's sort of 2 kind of reasons to think about this question. One is because, as I said at the beginning, what we actually want to know is which direction we need to go in the environment, right? And only the image can tell you specifically which path we need to walk down. The schemas and words are really just thought of as references. However, there might be some advantage to easily extractable spatial information that might be able to be processed by the brain a bit differently than the complex images. So to study that, we used fMRI using the same sort of set of stimuli and almost the exact same task as in study 1 that I told you about. But we had subjects only respond to catch trials. They were fairly accurate overall. So a quick demo of what this task looked like in the scanner. Similarly as before, they would see a spatial direction. They would see another spatial direction. Only rather than responding each time in this case, they would only respond when a cue came up telling them to indicate that this trial they had to respond for. They would never know when these catch trials came, so in theory, the subjects are trying to process the spatial direction within each stimulus sort of independent of the actual format of the information. So we had a few regions of interest that we might find the representation of sort of spatial direction in these different, in the brain, that is. And so some have been called the visual scene regions because they mostly respond to what I've been calling images, right? Exact images of visual scenes. So we considered that spatial directions might be processed within these regions specifically. On the other hand, another region that's intimately involved in a lot of this kind of spatial direction computation is intraparietal sulcus. So it's involved in mental rotation, but also in computing spatial directions relative to where one is currently facing. Now, we hypothesized that this region might compute a format-independent representation of spatial directions in the brain. Now, this might be an artifact of the way that we've designed the task, but that's a nuance that I can get to if people have questions about it. I'll also talk about EVC, early visual cortex, which we use as a control region to ensure that our stimuli were sufficiently controlled for various visual properties, which I'll gloss over and say they were. We analyze our data using multi-voxel pattern analysis, a brief technical interlude, which I'll blow through for those of you who are interested. The non-technical takeaway is, in essence, we're measuring similarity of spatial directions sort of across and within our formats, right? So that is how similar in the brain is a slight left image to a slight left schema. Now, the way this actually works in the brain is we extract a signal from each voxel in response to each spatial direction and each format. So we might have a pattern of activity in response to slight left schemas that look like this, and a pattern of activity in response to slight left words that looks like this. What we then do across all of our data essentially is construct a big correlation matrix where we see just how correlated is each of these patterns of activity. And we plot that correlation here in our big fancy correlation matrix, which is in essence how correlated are each of our spatial directions with each of our with every other spatial direction. And across each of our conditions, we're going to plot the correlation between them, which is going to give us, for each comparison of two formats, a big correlation matrix. And when we do that for all three possible combinations of our cross-format comparisons, this gives us one big average neural data comparison. And what's key here is you'll notice that the representation of spatial directions on this correlation matrix is essentially the comparison between the on diagonal, so sharp left compared to sharp left, compared to the off diagonal, so sharp left compared to everything else. So we can calculate what I'll call the discrimination index, which in essence are the correlations for the same direction minus correlations for the different direction. Now, first, I'm just going to do this all across format, right? So actually, the paper goes into a bit more detail on this, as you might imagine. But in essence, what we found is that spatial directions are similar across format in IPS, in this region, intraparietal sulcus, whose job it is to compute which direction we need to go relative to where we are facing. We did not get decoding of spatial direction in early visual cortex, good for us for control, nor did we get spatial direction decoding in any of our visual scene regions. So this is important because it suggests that what we're not doing when we look at schemas and words is converting them into some sort of scene-like representation, some sort of property of environment that might be what you see when you look at space. But, and to tie this into what is rad equivalent of IPS, somebody else answer that question. But format matters a great deal, right? So when you just look at the overall pattern of the data in the brain, and you look at all the variants that you can explain, spatial direction is actually just a small part of it. What drives the neural response the most is actually the format of the information. That is, whether somebody sees a schema or a word or an image, changes the areas of the brain that respond much more drastically than changing the spatial direction. Now, this isn't a surprise, but it is quite telling because it gives you some insight into what each brain region cares about. For example, although intraparietal sulcus did represent spatial directions across formats, IPS is also giving us a lot of information about the individual formats themselves. So this is a way of plotting the similarity, and basically arrows that are closer to each other are more similar in our correlation space. So this is telling us that for IPS, words are more similar to words, schemas more similar to schemas, and images more similar to images. Whereas for one of the scene regions that I told you about, OPA really is only going to care about distinguishing images from schemas and words, which it really doesn't care about distinguishing at all. Right. So this is a model of neural response that is telling us that these regions are deeply required for processing spatial directions in some cases, right? If you see an image, OPA might be crucial in helping you to extract that scene-specific spatial direction that you need. But when you see a schema or a word, you're much less likely to involve those scene-specific regions. One last piece of data on these signs is it'd be really great to know, right, if the spatial directions that we're presenting would actually be helpful for people who have more impaired cognitive apparatus, right? So to evaluate this question, we gave the same stimuli to a couple of patients who had posterior cortical atrophy, a form of Alzheimer's disease that principally impacts the parietal lobes, as I've highlighted here. And when we showed subjects these same stimuli, basically had them do a simplified version of the task. And what we found is that obviously control older adults did just fine. If you're cognitively normal, comparing these spatial directions, it's easy peasy. But in our two patients with posterior cortical atrophy, we saw drastic drop off for the image condition compared to the schemas and words. So a slight disadvantage perhaps for the schemas compared to the words in both of these cases. But it seems from these data that images really require this in-depth processing, either from scene regions that are then computing it to IPS, or in IPS itself. And this is work that we're sort of chasing up now. So the broad summary of this section is that signs offer easily extractable spatial information, which is then converted into usable spatial directions, perhaps in IPS. Schemas and words, on the other hand, may elide the depth of processing that is required by images, which is what makes them powerful supports for spatial navigation behavior, particularly in impaired navigators. All right, so we have two more tools to get to. These sections are a bit shorter, and then I'm looking forward to potentially answering some questions as well. So let's move right along and consider whether maps support spatial navigation. So first thing I kind of want to bring up here is that there is a wide variability in navigation ability. So those of you who've seen this talk series will have seen Mary Haggerty's talk from a couple of weeks ago, who talked about virtual Silcton. The only thing I want to mention about measuring navigation behavior is that it's actually really variable. And so one of the ways of measuring this is using a virtual tool that I helped develop called Virtual Silcton, which in essence is a large-scale virtual environment along which people learn different routes, highlighted here in red and yellow, and then have to report where different landmarks were in this environment. And in general, one of the nice properties of this is that it's actually based on a real-world environment. So Victor Skenazy painstakingly converted Temple's Ambler campus into a virtual model, which became Virtual Silcton. And it's a fairly immersive, and we like to think highly ecologically relevant navigation scenario. So apologies if there's a bit of lag in the video play, but it's a sort of what one might encounter in the real world, right? And so here you can see somebody is learning one of the main routes. There are 4 buildings along this main route they have to learn. There are 2 main routes, so they have to learn 8 landmarks. And we tell them they have to learn the positions of the landmarks and the relations between them. After they learn this navigation environment, we have them perform a couple of different tasks. One is an on-site pointing task where they're dropped next to one of the buildings. They have to point to all the others. And the second is this model building task where basically they have to drag and drop the buildings to the part of this on-screen box that they believe the building is located in space. So that's sort of the task that we're going to use here. And it's been widely studied So I won't go into too much detail here, but one of the key findings from virtual Silcton is that people are really variable in terms of how accurately they can learn this environment when we sort of constrain the way that learning happens, right? So we keep all that kind of constant, and then we measure how accurately people can learn the space, and we see really broad individual differences. They're actually broader than are being presented on this graph here. Ranging up to almost 90 degrees of pointing error. So that would be, something like where you think a building is in front of you and it's actually 90 degrees off to your right. So people are generally very variable on this task. But here, we're actually going to use it to see whether providing people with different forms of spatial support can actually help them learn this environment better. So one of the studies we ran was basically providing subjects with a map. So we gave them a representation of virtual Silcton that they could use along their second time encountering virtual Silcton. So they would navigate virtual Silcton the normal way once. We would then, we had a break, and then about a week later, they would come back. They would navigate virtual Silcton again the exact same way. Only 1/3 of the subjects received this map that you see along each of the times that they would get to travel through the route. The control condition followed the same exact 4 routes again, and a verbal direction condition received a written out set of verbal instructions that indicated where you would turn along each of the routes, but didn't have any images, didn't have any more sort of spatial information other than that. So here are the data pre-training from the model building task. So this was the one where they had to drag and drop the buildings into the part of the box where they thought they went. And what we're measuring here is the configural accuracy. So basically how accurate was their map overall. Now, pre-training, subjects were fairly variable, which is good. And across the 3 conditions, so this was before they'd received any map or anything. And so they're roughly equivalent to each other. Now, after training, after they received either the map or they followed the routes again, or they received the verbal directions, we saw a significant increase in the map condition, right? So giving people a map supports map making. Okay, well, that's great. But what we'd really like to know is, does a map actually help show you the way to go? So here is across the 2 different sets of pointing trials, which it didn't actually turn out to matter here. When you plot just the pointing improvement, so this is how much better subjects got at the pointing task, you can see that actually it doesn't matter what condition they're in at all, they did about the same. So comparing across these 3 conditions, it didn't actually help them to have a map. So here's where I'll bring in the first distinction between supporting navigation behavior versus improving it. Right? So in our case, merely giving somebody a map is not enough to help them infer which direction they need to travel in an environment from where they were. All right, so we're going to need to do a little bit more beyond that. So the way I'll sort of summarize this study, and this is ongoing work that we're doing as well. So maps provide configural knowledge of environmental landmarks and thereby support your ability to reproduce from a sort of top-down perspective that environmental information. But maps did not improve our subjects' ability of knowing the way to go. Yeah, exactly, Kate. And it fits Kate's personal experience. It fits my personal experience. And I am working on ways for that latter part. We're going to get there. All right, this story gets a little bit more pessimistic as well when we move on to compasses. And before I launch into this section, I want to know about how much time I should dedicate to it.
So we've got 15 minutes in theory to the end of the hour when you're due to speak, but I don't know, I'm not hosted before, so if Kate can comment, are we able to go a bit longer? I hope so anyway.
10-15 minutes will be fine.
Yeah.
Okay.
Yeah, that's what I thought. Probably overrun a little bit. So do carry on, Steve.
Awesome. Okay, so how do compasses support spatial navigation behavior? Well, I'm going to sort of use another toy example here. Let's imagine that you're in this field and you need to find your way home. Well, if you know the direct path to your goal, in the case of this wide open field, then you could just travel directly there, right? Easy peasy. Now, moreover, if you get a little disoriented here, but there's some sort of distal cue available, let's say a handy mountain range, that'll allow you to specify what we can call a reference direction, a direction that you can refer to and off which you can compute which way you need to go. So, aha, I see the mountain. I know that I need to travel a little bit to the left to get directly to my goal, right? So, of course, I'm presenting this information as a distal cue in the form of a mountain, but we can really think generally about what that sort of reference direction might be. So mountain might be the easiest way to understand it. Tends to be for me, but there are cues that can be provided simply by compasses that can also indicate the way to go. And the way those work is by providing a reference direction that then allow you to compute which direction, other directions of travel that might be relevant, right? And these sorts of reference frames have been very widely studied and show that they sort of capture the way that we tend to encode certain kinds of spaces. Although what kinds of spaces those are, I think is potentially an interesting question. So we might have something like a north-centered reference frame, and that's where you would encode your environment with respect to some reference direction like north. Now that could be quite helpful in an open field environment where you can go wherever you want, but we typically navigate in lots of different kinds of places, including places like these that make it very difficult to maintain a consistent reference frame because there's no long sight lines here, right? You can't see distal cues. And moreover, even if you can see them from some places, you walk somewhere else and then you can't see those distal cues anymore. And also in environments like this, the direct path to your goal kind of doesn't matter very much because we need to actually take a route to where we need to go, right? So it doesn't matter if I know that my location is 45 degrees to my right, if I need to take roads that take me in very different places from that, right? So what we might infer here is that actually a reference frame is not such a good way to support spatial navigation in an indoor environment like this. And this isn't some sort of hypothetical example. This is the UPenn hospital. So if you need to make it to your doctor's appointment, either on time or because there's an emergency, you need to know where to go. So this is not a hypothetical problem. So in order to study that, I provided people with this reference direction in a way that wasn't going to sort of obscure their encoding of any of the rest of the space, but would be a relatively unobtrusive way of getting information about reference direction. So we used a Vibrotactile Compass, which was strapped onto participants' arms. And the basic way it works is like this. So there was a series of 8 motors. So here's a schematic. The motor that's highlighted in red would indicate the motor that is vibrating. So you can imagine that this little strap was strapped onto this little fella's arm here. And so the motor that is closest to north is going to vibrate. Now, as the subject rotates through the space, the motor that vibrates changes, providing them constant source of information about where north is relative to the direction that they're facing. Now, the key question here is whether subjects are going to be able to use this information to more effectively navigate their complex indoor space, right? We're going to use the UPenn hospital here. So here we had 48 undergraduates. They had no knowledge of the hospital, and we pre-trained everybody on how that compass worked. Each subject learned 2 separated routes, one with the compass, one without, always counterbalanced across subjects. And along each route, we had them make those same sorts of pointing judgments. So they were at the beginning of the route, they walked along a route that I'll show you in a second, they make a series of pointing judgments, then they walk back, and then they make a series of pointing judgments again to all the same landmarks. So here is one of the routes. This is the first floor route. So subjects would start here at the beginning. We would always orient them at the beginning, regardless of what condition they were in, compass or no compass. So we'd always tell them which way north was. We would then lead them along a series of corridors, some of which had intersections, some of which didn't, almost none of which had windows to the outside space. Not that that would actually matter. We then had them learn, in addition to learning the route, they had to learn 3 what we call internal landmarks. So these are landmarks that were along the route in the hospital itself. In addition to pointing to all of these internal landmarks and having to learn the route, we also asked subjects about familiar external landmarks. So these were places around Penn or around the city of Philadelphia that all subjects indicated familiarity with, and that most subjects would know actually where they were. So in addition to learning about these internal landmarks, we asked them about these external landmarks. Just to give you a sense of where those landmarks were positioned, here is the University of Pennsylvania Hospital. Here are the external landmarks we chose around Penn, and here are the external landmarks we chose around the city of Philadelphia. And just for completion, after learning, at the end of the route, participants would point to all of the internal and external landmarks. We then had them reverse the route, so they led the way along the way back along the same route that we took them on the first time around. And then once they were back at the beginning, we had them make all those same pointing judgments again. And recall, at the beginning of the route, we had oriented them to north regardless of compass condition. So for completion, here is what the other route would look like with a different set of landmarks. And participants were disoriented between those 2 routes, so they didn't know how they were interconnected. So we had 2 different thoughts about the way that the compass might support navigation here. So on the one hand, we thought that the Vibrotactile Compass might help subjects encode the hospital routes more accurately with respect to a reference direction like north. In other words, even though these corridors kind of took them around a long and convoluted series of turns, the compass could help improve the representations of this of the hospital by giving them a reference direction in which to encode it. Now, on the other hand, we thought that the compass may not help them actually encode the space more accurately, but it may help them retrieve information that they already had encoded with respect to north more easily. So in this case, we thought that the external landmarks would be encoded with respect to north, but the hospital itself would be encoded in some arbitrary representation, right? Idiosyncratic to how the subject had actually encoded that space and not with respect to the compass direction at all. So first, overall, we found equal performance basically in route reversal. So having the compass versus not didn't really matter. Subjects were able to tell us which route we had taken by reversing it just fine. And although I'll point out that errors overall were very, very, very low. So subjects were pretty good at learning the routes and figuring out which way to go. All right, so now we can look at those external landmarks. So what we're going to contrast here is at the end of the route. Now, at the end of the route, remember, subjects had walked through this convoluted route. So the question was, could they basically indicate where those external Philadelphia and Penn landmarks were? And if you look at overall pointing error, what you can see is that the compass condition did better, right? So people wearing a compass were better at these external landmarks. Now, when they got back to the beginning, remember that basically here participants could remember where north was. So back at the beginning, when we had them point to all the external landmarks again, they're doing roughly the same. Now, for the internal landmarks, essentially we saw no difference between conditions at all here in pointing judgments, right? It didn't matter whether you had the compass or not. Participants were not more likely to encode, could not more accurately encode the locations of these internal landmarks. So essentially what we think is going on here is that subjects are able to recall where these external landmarks are because they've encoded them already with respect to north. So just to show what's kind of going on in subjects' head, what we wanted to see was whether or not these external landmarks were consistent with the representation of north. So what this analysis sort of does is that in maybe in an optimal configuration, subjects are making an error of about 10 degrees or so. And that would be consistent if the participant thought that north was roughly 10 or 15 degrees off, right, from where it actually is. But let's say the subject is wildly off. Let's say they think north is 100 degrees away from where it is, right? So a massive error in thinking where north was. Well, what we would expect in this case is that any landmarks that are similarly encoded with respect to north should then be rotated to line up and be internally consistent with each other. Right now, this isn't such a surprise for the external landmarks. The question is, what's going to happen for those internal landmarks? So what we're going to do to sort of calculate this is we're going to calculate each subject's best fit angle and then assume that this optimal rotation will give us where they think north is, in essence. Now, when we do that, we're going to get a reduction in error here because we're optimizing everybody's performance, but all we're doing is just performing a rotation of their pointing judgments. And what you can see is that when we perform this, we now completely eliminate the difference between these compass and non-compass conditions for the external landmarks, right? So this is suggesting that there is an internally consistent reference direction for those external landmarks. Now, what about for the internal landmarks? Well, here we actually don't see any appreciable changes at all. Again, we get this improvement, but the improvement is not systematic to the compass condition at all. And more to the point, we actually asked subjects in both conditions where they thought north was. And for the external landmarks, there's a really high correlation between where the subject indicated north was and their best fit angle that we calculated. However, the best fit angle for the internal landmarks was not correlated at all with where subjects thought north was. So this is all providing support for the retrieval hypothesis. This is suggesting that the compass is not, at least providing a vibrotactile compass in this form, is not allowing people to encode a new internal space with respect to a reference direction. Rather, it is giving them access to that reference direction, which they can use to recall information that they've already encoded with respect to it, but it doesn't help them learn new information this way. So now we're conducting a series of studies where we're bringing the compass into virtual Silcton using an immersive VR setup. So here you can see one of my research assistants demonstrating it here, where we're actually giving subjects in virtual Silcton a leg up, right, with a compass. Now, still not helpful, right? So the initial data that we've collected, if you just give somebody a compass, sort of the same thing as encoding a sort of internal landmark here, right? They didn't encode Silcton with respect to north, and so just giving it to them does not necessarily make them better overall. But what this is allowing us to do is to conduct a much more controlled set of experiments and do some more in-depth training to actually show how compasses, if they even can, might be able to more effectively support navigation behavior. So how do compasses support navigation? Well, compasses provide a reference direction that aids with retrieval, but compasses did not improve our ability to learn new spaces. As work that's going on in my lab now, we're contrasting compasses with more naturalistic directional cues. So this is an actual screenshot from one of the studies that we're about to launch. And one of the questions I have about this is that compasses are really this sort of, regardless of the format they're in, they're very far removed from our actual own perceptual experiences of the environment. And so it could be that more naturalistic depictions of distal cues might lock in that reference direction more easily for subjects and allow us to scaffold some training in. We can also compare visual and vibrotactile, but I don't have time to talk about that today. So going back, just a couple quick conclusion slides and then I'll be quiet. So I think in considering supporting versus improving navigation, it's really important to consider what our navigational goals are. Right? These tools, I think, can very effectively support navigation behavior. And if our goal is to just give spatial information that can be easily extracted, this is really important to know for, say, older adults or people with accessibility problems. It would also be helpful to know for people who want to become lost, right? If they know that they can have the support they need from a map or a compass, that might be all they need. But I think what's a little bit more difficult question is knowing when we want to support navigation behavior versus when we want to improve it. What is required for each one of these is going to be very different. and when you might want to do which is also an important consideration. So I'll leave us with a couple of areas of emphasis that I think are important. So if you're considering supporting spatial navigation, you should emphasize design, what is easy for people to use. You also want to think about task. What is the exact information that people need in order to get where they're going? Now, if we want to do the harder thing and improve, we should think very hard about how we train people on using navigation tools, because exposure to them is clearly not enough, although perhaps people can do better in different navigational situations. And lastly, just a hand wave at what is sort of a pillar of my overall research program, individual differences are also crucial to consider in improving behavior. If you don't know what people are bad at, you have very little sense of what to push on to get them to get better. So I'll leave you with poor Frank Worsley here, who perhaps if he had been trained on using GPSs rather than sextants, he may have ended up with an escape route that looks something like this. Although if he were following a GPS, I'll note he would still have gotten to where he was going. So would he be the worst navigator for it? I'm not so sure. So navigation tools support navigation by transforming the local environment into orientation and location, improving navigation. Stay tuned. All right. I'd like to acknowledge some of the collaborators and some of the people in my lab who've done this work, all of my funding sources, all of you. So thank you. Apologies for going a little bit over on time, but thank you, Kate and Hugo once again, and the audience for hearing me rant on this.